Hi everyone, thank you for joining me. My name is Asad Mirad. I will be presenting peak rain forecasts for the US High Plains amid withering waters. This is published work and the proceedings of the National Academy of Sciences, and I was lucky to have many great, awesome co-workers with me on that paper. Here, I will be introducing a framework that utilizes the link between groundwater withdrawal and crop production to forecast. I want to start by acknowledging my funding sources, which include the National Science Foundation, the Unidel Foundation, and the University of Delaware. The initial discussions for this work started at the Ettersberg Ecohydrology Workshop in Germany in October 2018. I particularly want to thank Delphis Levia, who you see on the bottom right, for organizing the workshop and sourcing the funds. Groundwater depletion occurs when groundwater withdrawal exceeds recharge. On the top left, you see a global map of recharge rates, of groundwater recharge rates, which depend on the local climate. Areas with blue coloring have high recharge, whereas areas with orange coloring have low recharge rates. On the top right is a global map of withdrawal rates, and areas with high withdrawal rates are colored in red. The difference between withdrawal and recharge yields the depletion global map. And I highlight here 4 regions that have particularly high rates of groundwater depletion. This map shows the reliance of irrigation on groundwater resources. Areas colored in red rely more on groundwater. And these 4 regions I've highlighted before are colored in red. This highlights the link between groundwater withdrawal and irrigation for crops, and we will be using this link to forecast crop production. I will particularly be focusing on the High Plains region. For desirable characteristics, I will be explaining in the next slides. The High Plains has latitudinally different levels of groundwater depletion, as shown in the figure on the left. This figure shows changes in water levels from 1950 to 2007. Areas with pink coloring have higher water level changes, indicating high depletion rates. As one goes from the south to the north, for example, in the Texas High Plains, we see a lot of pink, indicating a lot of depletion, whereas in the north in Nebraska, there's barely any depletion occurring there. There are also trends spatial trends and recharge rates, with Nebraska having very high recharge as indicated by the blue and green coloring, whereas as one looks to the central High Plains in Kansas and the southern High Plains in Texas, the recharge rates are lower. And so we can split the High Plains into 3 regions. There's the northern High Plains, represented by Nebraska, the central High Plains represented by Kansas, and the southern High Plains represented by Texas. So we want to quantify these differences throughout these 3 regions. At the top, you can see 3 side-by-side figures showing the trends in harvested or planted irrigated acres or area with time. On the left, there is Nebraska. Irrigated area is still increasing today. In the middle, there's Kansas. The irrigated area has plateaued since the 1990s. And on the right, there's Texas. And the irrigated area has been fully developed since the 1960s. We also see the trend in recharge rates. Here they're quantified for the 3 regions, the northern, central, and southern High Plains. And there's also a gradient in the stored water throughout these 3 regions. We have the data now, and we have a quantitative view of the differences. How do you go about modeling the groundwater withdrawal crop production interactions in these 3 regions? We start by an analogy to peak oil. As you can see in the figure on the left. The figure on the left depicts the peak oil phenomenon. Hubbard in the 1950s predicted the peak in US crude oil production decades in advance. The curve he used, which is what you see on the left, is the derivative of the logistic function. The success of the Hubbard curve for US crude oil has inspired using a logistic function for non-renewable resources like groundwater depletion. Similarly to the peak oil concept, there's the peak groundwater production concept, and this plot shows the production of groundwater with time. To that, I add trends in groundwater-based crop production. And it also suffers from a peak called peak grain production, or peak grain for short. And there's a lag between peak water and peak grain. So can we develop a mathematical framework that captures these peaks and peak water and peak grain and the lags between them? One way we can answer this question is a predator-prey analogy. In the blue rectangle, you can see the accessible groundwater. The accessible groundwater is the groundwater that is available under the irrigated land area and that is deemed economically viable for withdrawal. It is the prey. In the yellow rectangle, we can see the annual crop production, and it is the predator. There are two inputs to accessible groundwater. First, there's the irrigated area expansion through the drilling of new wells. And there's also the recharge rate through percolating rainfall and surface water expressions. There's also feedback terms between the accessible groundwater and the annual crop production, and a depreciation term that sets a limit on the growth of the rate of crop production. Here I show the analogy or the correspondence between the Lotka-Volterra predator-prey model on the left and the groundwater crop production equations on the right. I will now compare the two. The two highlighted terms represent the feedback between groundwater and crop production. The term in red represents groundwater withdrawal, and the term in green represents the change in the rate of crop production as a result of groundwater withdrawal. These terms are analogous to similar terms in the Lotka-Volterra equations. This highlighted term in the red rectangle represents the depreciation term and is due to, for example, a stagnation in yield improvements due to irrigation and fertilization, or limits to crop density per unit area. The difference between the Lotka-Volterra equation and the equations we use here is the regeneration of the prey. The regeneration of the prey in the Lotka-Volterra equations happens because of reproduction. In the case of groundwater, however, the regeneration is due to external forcings, including the recharge rate and the drilling of new wells through irrigated area expansion. And these are represented by the red rectangle. Now I will show you some results, starting with the northern high plains in Nebraska. In blue are shown the groundwater withdrawal rates with time, and in red, the groundwater-based crop production. The dots are data from the US Geological Survey and the US Department of Agriculture. Because of its high recharge rates, we expect groundwater withdrawal to increase slightly in Nebraska from today to 2050, and crop production to increase more significantly. Kansas has lower recharge rates than Nebraska. And we see a peak water around the 1990s that was followed by a steady decrease in groundwater withdrawals. Peak grain has plateaued recently, and we predict that this will also be the year of peak grain, or the time frame of peak grain. So we expect a stagnation in the rate of crop production to levels that are present today, and then a slight decrease until 2050. There's also a lag between peak water and peak grain of about 2 decades in Kansas. In Texas, we were surprised to see a rebound in the trends of groundwater withdrawal and groundwater-based crop production. There are 2 peak waters and 2 peak grains, and the lag still existed between the two. The lag after the rebound was longer, and we also realized or noticed that the rate of crop production per unit groundwater withdrawal has also increased after the rebound. But why did this rebound happen in Texas? An explanation is the rate of sprinkler adoption with time, which is what we see in this bar graph. This is the sprinkler adoption in the Texas High Plains, and it has increased steadily, especially in the 1980s and the 1990s, when we saw this rebound in groundwater withdrawal and crop production. This also agrees with the increase in the water use efficiency of crop production after the rebound, because sprinklers improve the efficiency of water use. There is also a particular trend when it comes to irrigated area by crop. These two figures show the percent of the groundwater irrigated area for different crops. For Kansas on the left, we see the percentage of the area for corn increasing since 1985, and that of sorghum decreasing. And the same can be seen for Texas for even a longer time. And since irrigated corn has higher yield than irrigated sorghum, crop production was still able to increase even after the occurrence of peak water. We can also arrive to conclusions by comparing the normalized trends. On the left, we have the groundwater withdrawal ratio plotted against the years since peak water in each region. The groundwater withdrawal ratio is the ratio between the groundwater withdrawal rate and its value at peak water. We notice that in more sustainable cases like in Nebraska, the trends are very asymmetric. Whereas at the other end of the spectrum, in Texas, before sprinkler adoption in solid blue, we have very symmetric curves reminding us of the Hubbard curve. We can also see the crop production ratio with time. The x-axis is also the years since peak water. The crop production ratio is the ratio of crop production to its value at peak grain. And we can here visualize the lag between peak water and peak grain. And it is also smaller for the Texas case before the adoption of sprinklers and larger for Kansas. And so when the agriculture crop production system is more sustainable, the trends are less symmetric and the lag between peak water and peak grain is larger. To end, I'm showing forecasts for groundwater-based crop production in 2050 and comparing those to their values in 1980 in yellow and 2016 in orange. While Nebraska had similar rates of groundwater-based crop production as Kansas and Texas in 1980, in 2050, it is projected to have 10 times the amount of crop production from these two other regions. This assumes, however, that no innovations are going to enter the dynamics between groundwater withdrawal and crop production in the High Plains. Thank you for listening to me. This is the end of the presentation, and I look forward to answering your questions.